Well, we took a little bit of a detour because we started talking off earlier in the semester about hydrocarbons and we looked at alkanes. And I guess you could kind of consider alkyl halides maybe a little bit into that, but we're going to keep on going with just functional groups that contain carbon and hydrogen only. And so now we're going to be looking at alkenes. And we've talked about alkenes a little bit, but these are hydrocarbons that contain a carbon-carbon double bond. And we looked at the nomenclature of those briefly in a previous unit. And so I just want to talk a little bit about alkene structure and another way to designate certain alkenes. Because we've talked about the difference between cis alkenes and trans alkenes. So this here is cis 2-butene, and this is trans 2-butene, because the um, groups, the carbon groups on either side of the double bond can be going in the same direction, or they could be going the opposite direction in this case. Now, not all alkenes can be designated cis or trans. Remember, we have to have two different groups on one on each side so that if they're the same group, then you can't really tell what is cis or what is trans. And this works great if the groups you're comparing are carbons. But what happens if we deal with compounds, or with alkenes, I should say, that the groups are not, we'll make that a methyl group, um, all carbon groups. So like in this case here, we have um, a chlorine there. So how do we handle something like this? How do we designate the cis or trans? Because, are we saying the methyl groups are trans to each other? Or are we saying the one methyl and the chlorine are cis to each other? So it gets a little kind of confusing when we're talking about groups other than carbon groups. And so we use a different notation, kind of like cis or trans, where we look at the groups, but we use E versus Z. And in order to do this designation, what we are going to start off is by using the RS priority rules. Now, we're not going to designate carbons as RS, and we're not even going to count like 1, 2, 3, and 4 like we did previously. But what we're going to do is compare the two groups on one side of the alkene and then the other side, and we're going to judge the higher priority groups on each side. So let's just look at the green side I highlighted there and compare carbon to chlorine. Now, if I were going to do the priority rules, which one of those would have the higher priority? Well, since chlorine has a higher atomic number than carbon, it would get a higher priority. I'm not even going to use a number 1, 2, or 3 designation. I'm just going to say the chlorine is higher than the methyl. Now, if I go to the other side, the yellow side, I'm going to compare carbon to hydrogen. Now, carbon has a higher atomic number, so it would get a higher priority over hydrogen. So if the two groups of higher priority are going in the same direction, we give that the Z designation. So we would call this Z 2-chloro 2-butene. And this tells the reader that with that Z stereochemistry, what direction the chlorine and the methyl should be going in. Now, if the groups of higher priority are going in opposite directions, so again, here the chlorine is higher compared to the methyl, and this methyl is higher compared to the hydrogen, we give that the E designation. So we call this E2-chloro 2-butene. And so where cis and trans will start to fail when we're dealing with groups other than carbons, The E or Z could be used at any time. We could use E or Z on our first examples here. Like this would be Z2-butene, and these would be E2-butene. So E or Z works anywhere. Cis or trans only works for alkenes if the groups you're dealing with are carbon groups. So let's kind of jump right into what we're going to be talking about for most of this unit, and that's the reactions of alkenes. One of the most typical reactions alkene undergoes are known as addition reactions. Now, let's just kind of recap a little bit what we've done with alkenes so far. In the previous unit, we made alkenes through elimination. Okay, so that was unit 7. Now, what do we do with these alkenes once we make them? Well, a lot of times the easiest thing, or the most common thing, I should say, is that we add to the alkene in a process that we call electrophilic addition. And what that means is that the alkene, and more specifically, the pi electrons in the double bond, act as a nucleophile and make a bond to an electrophile. So here's kind of a generic reaction. We're going to take this alkene and we're going to react it with this compound, AB. And one carbon of the double bond is going to get A, and the other carbon of the double bond is going to get B. And we'll talk about a little bit later which goes where and, how to deal with all of that. And there's a lot of different things that we can add across this double bond. So we're going to look at all of these reactions. We're going to look at adding H and X, H and OH, H and H, X and X, X and OH to both sides. So we're going to look at all of these, and they fall under the realm of electrophilic addition. But let me talk a little bit about why this reaction even happens. The driving force for this reaction is we're exchanging a weaker pi bond for 2 stronger sigma bonds. So the product ends up being more stable than the reactant. And if we're going to draw a reaction coordinate for this or an energy diagram, it would look a little something like this. We'll start with our reactants here. And then we get down to our products. Now, some of these reactions are actually are reversible. So I'm going to change my arrow up here and instead make it an equilibrium arrow, where going to the product side is the addition and going to the reactant side is elimination. And I want you to look at this energy diagram and imagine starting at the products and going back to the reactants. What would it take to do that? We got to get over, this very large activation energy barrier. These reactions are reversible with enough heat. And what that means is the elimination direction, or going back to the reactants, is favored by high temperatures. And the addition is favored by low temperatures. Although most of the time you'll probably will just see me use a single arrow instead of an equilibrium arrow. But just you'll kind of want to make a note as we go along. You'll see that some of the reaction conditions for addition are actually set pretty low, um, simply to maximize going back or going to the product instead of having it go back to the reactants.